So with the shortage of time, maybe we will move to the next speaker, which is our poster presentation with Dr. Srinivas Puli. So Srinivas, can you share your slides? And he will be talking about nanoscale polarization switching of lead-free materials.
Are you able to see my screen?
Yes, we are able to see you.
Hello, everyone. Thank you very much for the opportunity. So today I'll be talking on artificial multiferrite materials and the nanoscale polarization switching of combination of perovskites and spinels. So I'll directly go to the talk. So as we all know that materials which exhibit both ferroelectric and ferromagnetic or ferroelastic ordering in single phase or composite materials will have a property called multiferroicity. So these materials are potential candidates for electronic applications such as data storage, spintronics, and various other applications. The coupling especially between the ferroelectric and ferromagnetic or ferroelastic ordering opens new opportunities in this area. So we have a very small area of single phase materials for these applications. So we thought of combination of different ferroelectric and ferromagnetic materials to obtain the multiferrosity in these materials. So however, there are a few challenges with the single phase multiferrite materials. Only few are existing, and more explored is bismuth ferrite, which is having a TC of 1100 Kelvin. So, but with the single phase multiferrites, there are difficulties to fabricate single phase multiferrite materials because of the high leakage current behavior, dielectric high losses, and low magnetoelectric coupling factors, and low temperature phase transitions. So then we thought of going for artificial multiferrites. So where we have combined the ferroelectric and ferromagnetic phases. So ferroelectric phases with the barium zirconium titanate and barium calcium titanate, it's a solid solution. And when we have taken magnetostrictive and ferromagnetic CFO, which is having the inverse spinel structure, whereas the ferroelectric phase has perovskite structure. So the combination of sandwich structure is we made using the pulsed laser deposition technique. We made the sandwich structure on platinum silicon substrate. We have taken the ceramic targets of both ferroelectric and ferromagnetic phases, and then we made the thin films deposition using PLD. So whereas we made all the structural and morphological characterizations. So for electrical measurements, we have taken the metal insulator metal configuration, where we have used the bottom electrode as platinum, the substrate itself, and the insulating materials are sandwiched like ferroelectric, ferromagnetic, ferroelectric. So that's why we call it as the tri-layers. So then we have got the excellent room temperature phase properties for all the individual films and as well as the combination of the tri-layers. So then we have measured the ferroelectric measurements and as well as ferromagnetic measurements at room temperature at different frequencies. And to check the thermal stability of these films, we have made both ferroelectric and ferromagnetic measurements from low temperatures to high temperatures until the phase changes from ferroelectric to paraelectric in case of ferroelectric materials, and as well as the TC of ferromagnetic materials. So as I said, like the thermal stability is also found out using the dielectric properties. So where these dielectric materials have shown very low losses and as well as the low leakage current behavior. So then we went to the nanoscale polarization. We have used the PFM measure technique to measure the nanoscale ferroelectric majority and as well as the ferromagnetic properties of these multiferrite films. So usually PFM is a variant technique of scanning probe microscopy, so which is an important technique to visualize the piezo response of the films at nanoscale dimensions. So which involves the application of voltage between the conducting tip and the sample. So here you can see the schematic diagram, and we can measure both ways, like out of plane and in plane measurements for the films. So then we have obtained very excellent PFM behavior with the ferroelectric and piezoelectric and as well as piezomagnetic behavior for these films, and we confirm that you can see from the images of the amplitude and phase, we have the bright and dark combination contrasts, and as well as which also confirms the square patterns with you can see the images here. Perfect square patterns were recorded for the PFM from the PFM measurements, as well as we can see at nanoscale, you can see the hysteresis loops for both amplitude and as well as the phase, which shows the perfectness of these films. And we have already also made the polarization displacement measurements with large values of 1175 picometer for volts for these materials, and especially the multiferrite materials with magnetoelectric coupling is most important for the applications. So these films have shown excellent and extraordinary data for even for the magnetoelectric coupling. Then, as I said, like the perfect square patterns were shown, and in conclusions, I say that these lead-free ferroelectric and ferromagnetic combination of tri-layers are fabricated successfully using the PLD technique, and excellent multiferrite behavior with high saturation polarizations and as well as high saturation magnetizations were recorded. Excellent magnetoelectric coupling was observed, and the PFM contrasts were seen, and the excellent electric and magnetic domain patterns were visualized using the PFM technique and MFM studies also. Because of the time constraints, I am not going into the deep. So nanoscale switching and square patterns with opposite voltage confirmed the ferroelectric and piezoelectric nature and as well as piezomagnetic nature of these artificial multiferrite films at nanoscale level. So the tri-layer nanostructures are applicable for multifunctional applications. We have also measured from different properties for different applications. So which can also be used for photocatalytic applications and as well as energy storage and data storage and etc. So here I conclude that from my studies, and I thank you committee of CheMET and especially Dr. Kishore, Professor Kishore, for giving such an opportunity, and thank you all. These are all are our collaborators, SAS Technologies, so many others. Thank you for your attention. If you have any questions, I'm open to take the questions. Thank you. I hope I'm in time. So I'm not getting your voice.
Sorry. So I have a quick question regarding the PFM.
Sure.
Do you use this is the typing mode still, not the contact mode, right?
No. This is tapping mode, yes.
And this is without applied electric field, right?
Without application of we have lock-in amplifier is attached actually.
I see. Okay. So when you apply the electric field, generally you can see the heads. Probably it grows the ferroelectric domains or something, or
yeah. Because of the time constraints of the poster presentation, okay. I'm not going into deep actually.
All right. Okay.
Yeah, we have done different sort of measurements, and these films were tested at reputed laboratories like Nebraska and even in the Portugal, Professor Kolkin's laboratory, and as well as Professor Alexei Gruverman, who are top in the world for PFM measurements. And time-dependent studies also done on these samples.
Thank you very much, Professor Puli. Let's move to our next speaker, Professor Luis Edrino Armenteros.
Thank you, sir. Thank you.